we're going to call this as alpha 1 and alpha 2.
Yeah.
All right. So part A, you're trying to represent 1, 2 as a linear combination of these two basis elements. So A times the first one plus B times negative 5, 3. Which means, well, if you multiply A, multiply B, add them together, you get 3A minus 5B, and then negative 2A plus 3B. So we have a system of equations, 1 equals to 3A minus 5B, and 2 equals to negative 2A plus 3B. Now, I guess the quick way to do this is to multiply this by 2 and multiply this by 3 so that the coefficients match, both become 6. So 2 is equal to 6A minus 10B, and 4, no, this is 6. 2 times 3 is 6. 6 equals to negative 6A plus 9B. Add them up, and you get 8 equals to negative B, so that B is equal to negative 8. Take that value and plug it back into any of these equations. Let's plug in here. 1 equals to 3A minus 5 times negative 8. That's 40, subtract negative 39 equals to 3A, so that A is equal to negative 13. Okay? So we now see that this value should be negative 13 and this should be negative 8. Therefore, 1, 2, if you use the basis vector B, the matrix representation would be negative 13, negative 8. Is this right? Is what you got? Okay, great. So that's part A. Now, part B and C, we're trying to get the transition matrix and use this to get the same result. And before I move on to do the second thing, let me try to explain why this formula makes sense. See, let's see. First of all, what is alpha 1 under A? That's a simple question. Let's see if you understand what we're doing. What is alpha 1 under the basis A? It will be 1, 0, right?
Oh, because there's no alpha 2, so at the moment, yeah.
Alpha 1 is 1 times alpha 1 plus 0 times alpha 2, right? So if you represent alpha 1 using basis A, which is A is made of alpha 1 and alpha 2, right? It will be 1, 0, right? Let me ask, what is beta 1 under basis B?
0, 3,
It's again 1, 0. Because what is beta 1? Beta 1 is 1 times beta 1 plus 0 times beta 2. Right? So if you use basis B, it's 1, 0. Okay. What's not clear is what is alpha 1 under basis B. Right? But then, let's think about, let's say we did get these values. Let's see what this is really doing. Suppose we have this matrix computed. Let's say we do have it. Okay? Now, if I multiply this, this is I A to B. That's what this is. That's what I'm claiming. So if I multiply alpha 1 A, this should be getting what? Alpha 1 under, I'm using this formula. If I multiply I to V, what does this do? It doesn't change the vector itself, it just changes the basis representation. That's what this matrix does, right? Okay. So what do you get if you multiply this times this? You get alpha 1 basis B, right? That's what you get. But look, this is what? We figured out that this is just 1, 0, isn't it? But then if you multiply a 2 by 2 matrix with 1, 0, what does it pick up? When you do this times this times this is not included in here because you get 0, and this is just 1. So you just get this portion times 1 as the output, which exactly agrees with this. Do you see now why this matrix would satisfy that this matrix would do exactly what this is required? Right? Same thing, the alpha 2 of A should give you alpha 2 of beta, but then alpha 2 of A is 0, 1. If you multiply 0, 1, it will ignore this one and just give you this as the output, which is exactly that one. And then if you have in general any composition of those two, then it will be the same matrix with the other one, because you've transformed the basis vectors correctly, and the other ones just follow. Right? So that's why this formula makes sense. Okay. So once you are convinced that this is the formula, now let's try to calculate alpha 1 beta, which means I want 1, 0 to be represented as some combination of 3, negative 2 plus negative 5, 3. And that means 1 should be 3a minus 5b, and 0 should be negative 2a plus 3b. Same deal, multiply by 2 and multiply by 3. Add them up, and you get b, negative b equals to 2, so that b is negative 2. And you plug it back in here, and you get a as what? Negative 3?
Yeah.
So you get that as this. This would be negative 2, negative 3. And you do the same thing for the other one. Alpha 2b means you want to represent 0, 1 as a times 3, negative 2 plus b times negative 5, 3. But that's exactly the same calculation, except that, sorry, let me be just a little bit lazy, okay? 0 and 1, right? That's what we're doing. Times 2 gives you 0. This will be times 3 is 3. So you get what? 3.
So should I change it?
So b would be negative 3. If you plug in negative 3 here, that's positive 15. Subtract, you get negative 5.
Oh.
Is that right? Or did you get something else?
Yeah.
B is negative 3, so you get negative 5? Okay. So alpha 2 beta would be, basis B would be negative 5, negative 3. Okay? So that's what we got. Is that okay? And another way I suggested was, which is the quicker one if you know. So from these two we get that the matrix is negative 2, negative 3, negative 5, negative 3. That's what you get. The quicker one would be actually, you know that B to A is simpler, isn't it? Right? What's that? B to A is,
Beta 1.
Beta 1 with A, beta 2 with A, right? But I know what this is. It's just this under this, which is 3 and negative 2. Right? The standard basis is really easy to compute, right? This with this. Right? So what you have is 3, negative 2, and negative 5, and 3. That's what you need. Right? Now, how do you get this from here? What do? You just use the fact that this is the inverse matrix of the other one, right? You agree? B to A is the inverse matrix of this one. So you just take the inverse of this. What do? It's 1 over 3 times 3 is 9, minus negative 5 to the negative 2 is 10, right? Switch these two around, which doesn't do anything, and then sort of negate these two. the 2. And because this is 1 over -1, this is just -3, -5, -2, -3, which is exactly the same thing. So that would happen much faster. Okay? Yes?
I thought alpha 1b was -3 over -2. I thought.
Oh, sorry, I got it backwards, sorry. Yeah, which is here, right? Sorry. -3, -2, -3, -2. Okay? Yeah. All right. Oh, you weren't saying that before?
No,
No?
I was getting it.
Oh,
You
okay,
switched
okay.
it.
All right.
Okay.
So that's the correct one. Yeah, this verifies that this is the correct one. Yes,
So like, can you give an example of like an application of this?
we will, yeah, except that we don't have enough time.
Oh,
All right.
I'm just saying like in words, like
The next
where
episode.
where would we see this in your life, I guess?
So the direction we are getting to is we have, if you're given a matrix A, then you can choose a basis so that the matrix A looks simpler in that basis. Okay? That's the idea. We'll get there eventually. Okay, it's too early right now. Okay, all right, so in part C, what do we have? -3, -5, -2, -3. And you multiply 1, 2. And if you do that, you get exactly -13 and -8. So it agrees, this formula, when used for 1, 2, it agrees with the answer to. Yes?
I have a question. So why
Yeah.
did we, like, in the previous example, why did you,
We did a little bit differently, right? We took a bit different approach because I just wanted to use the first principles.
okay.
Here we're using a formula, but there we're just using the first principles. You should be.
This is a shortened version.
It'll be like shorter version.
Okay.
It makes things simpler, right?